So I'm going to talk very quickly about what robots are. Many people have got a notion of what robots are, but often that comes from Hollywood and fiction rather than from reality. The reality of robots today is that most of them are machines that work in factories. And the only impression to take away here is that factories are a very well-organized environment. Robots are very good at building cars and computers. They've been doing it for 60 years. And they allow us to build high quality products at low cost. So this is the natural home of robots. This is where they grew up. And robots are used all around the world. This chart shows the number of robots per 10,000 employees in industry. And we can see that a lot of countries, Singapore, South Korea, Germany, have got a very high penetration of robots in their workforces. That doesn't mean that they have high unemployment. So unemployment and robot population density are not correlated at all. Australia is about the middle of the pack in terms of its adoption of robot technology. And robot adoption is increasing, particularly in the Asia area. That's what the graph on the right-hand side shows. And predominantly these kind of robots are used in the automotive industry and electronics industry. That's where traditional robots are. Whether you can see this video or not through Zoom, it just shows what robots can do. They're very accurate, they're very fast, and they are relentless. They just go 24/7, they don't get tired, they don't make mistakes. But they're not very good at many things that humans are very good at. So this is a very painful video showing a robot attempting to fold a shirt. And the video goes for 20-30 minutes. And a very young human could fold a shirt way better and way faster than what a robot can do today. So robots can do some things very well, and they can do other things actually very poorly. And that's what robotics researchers are trying to do, trying to close that gap. So the robots that I've showed you before are fixed in place, and that's useful for some jobs, but the real value of robots comes when they can move around the environment, drive themselves around. So this started in factories with forklift trucks and so on that could move around a warehouse or move around a factory to move material from one place to another. Where a machine that's fixed to the ground can only access things within its arm's reach. These things have got a very large reach. Amazon as a company have really finessed this. They own over 200,000 robots, which are used to move material around their warehouses, which is what allows them to be, the most cost competitive reseller on the planet. A huge adoption of robots. There are more robots than anybody else on Earth. And that's been a massive internal investment on their behalf. So there's a whole class of robots, which is what I've spent most of my career being associated with, and which call these field robots. So these are robots that are not in factories. They're out and about in the real world. They're doing tasks that are traditionally done by humans driving machines. So here's an example of robots at a port that can pick up containers and move them around. So those orange machines you can see there are not driven by humans anymore. They are completely autonomous. They can be used for construction, and they can be used for demolition. And the advantage here is these are tasks where it's perhaps a bit dangerous for human beings to go. So robots can do these jobs instead of putting people in harm's way. Now, some of these robots might actually be remotely controlled. They may not be completely autonomous, self-actualizing. There may actually be someone sitting out of harm's way with joysticks moving the machine which is in harm's way. So that's a very valid type of robot. We call that a telerobot, remote robot. Field robots for undersea operations, and whether that's for marine science or whether it's for servicing the oil and gas industry. Another important class of robots that are working in the field. Forestry is another really big example. Bomb disposal, various other, I'm afraid, military applications of robotics fall into this category of field robots. And in Australia, of course, the big one is mining. And there are a large number of completely robotic trucks moving around various mine sites in Australia on the surface mines and in underground mines. This is all the remit of field robots. Agriculture is an area that we've done a bit of work in at QUT. So this is a field robot that we built that looks for weeds and removes them in broadacre agricultural crops. Another example of a field robot is planetary exploration. And we send robots to remote locations like Mars and the Moon because it's not cost effective to send humans there. But I think that same argument probably applies to the Antarctic, where we can send humans there, but it is costly, it is dangerous, and perhaps humans augmented by outdoor robots could gather more data than humans alone can do. Robots can move not just with wheels, there's all sorts of modes of locomotion for robots. So this little robot is able to climb and walk using legs. Here's another robot which has got legs and is able to run much, much faster, made by a Boston company called Boston Dynamics. Here's an example of a robot developed at CSIRO in Brisbane. This is a hexapod robot, so it's a bit like an insect. It's got very long legs, and it lifts them up and puts them down and can move across the landscape. A machine with 6 legs is very, very stable and able to walk over incredibly uneven terrain. So, you know, rocky terrain, maybe icy terrain. Here's an example of a field robot developed at Carnegie Mellon University in Pittsburgh. It was fielded in the Antarctic. Its job was to look for meteorites, which apparently rain down on Antarctica as they rain down on the whole planet. But in the Antarctic, they're easier to find if they're fresh because they're a black rock against a white background. So this mission, more than 10 years ago, able to find a number of fresh meteorites with this robotic machine which roamed over the Antarctic surface. So these are just awesome examples to give you an idea of what robots are capable of doing today. Robots not only have legs and wheels, they can fly. So people have built robots that look like blimps, look like helicopters, drones of all shapes and sizes. And then there's a whole class of robots which are either like robot boats or robotic submarines, which is what Matthew will talk about next. Here's an example, which I hope you can see. This is a drone that's capable of doing physical sampling. So this drone does water sampling. It flies out over a lake. It drops the end of the sampling hose into the water. It slurps up a water sample and then flies on. So instead of having to send somebody out in a boat to collect a physical sample, the drone can collect a physical sample. And I think this is an interesting possibility of what we might be able to do within SAEF, is to use robots, not just to measure things, but to collect physical samples and bring them back. Another robot that this is a robot I showed before, we created at QT for agricultural purposes. This robot is able to not only do its task, but it can automatically bring itself back to base. It can recharge itself, refill with electricity, refill with herbicide, and go out and do another mission. So it needs no human intervention to do very long endurance missions. This particular robot, as it's rolling over the ground, it's got cameras looking down, and we use AI techniques to recognize the individual plants that it's seeing, classify them and count them. And for the weeding application, if it's a bad plant, then we will either spray it or chip it out of the ground. The same robot, the data that comes from the cameras, we can build these into massive mosaics. So we can integrate the view from all the pictures of the robots rolling over the terrain into a huge image, huge color image, a huge 3-dimensional image, which we can use to subsequently analyze. And that's perhaps another possibility of what might be useful in the SAEF application. Last robot example I'm going to show is a robot developed in our lab, and this is a robot that picks capsicums. So here you see the robot. It's got a 3D camera on the end. It's moving around. It builds up, but you can see on the left a colored 3-dimensional representation of the scene. And once it's got that, then it can recognize where the capsicum is and plan a motion to come in, grab it, separate it from the plant, and put it into a bucket. So these are the sorts of capabilities that robots have. They can move through the environment, they can recognize things, they can perform physical actions. So Johan has given a good introduction to what we can do with sensors embedded in the environment. And there's actually an interesting trade-off between the deployment of sensors and the deployment of robots. And it's a trade-off in space and time. So elaborate, if we embed sensors in the environment, they can measure things, whatever quantity you choose to measure with your sensor, be it chemistry or temperature or physics or light, we can measure them at a very high rate. But to cover a very big area, we need to deploy a lot of sensors, and that leads to issues with cost. So perhaps we have to skimp on the quality of the sensors that we deploy at multiple locations. And we also have some challenges with communications. Now, alternatively, is we could put the sensors on board a robot, and the robot can tour around the environment and make measurements. Now, that means that you've only got one sensor, so you can afford to spend more money on it. You could have one good sensor and use the robot to take it around the environment to make the measurements that you want. But you lose the ability to measure a quantity at many places simultaneously across space. The robot moves through space, and that's the trade-off between in-situ sensors and robots. But a robot is able to potentially collect and return physical samples, be that of moss or some organism growing underneath an ice shelf or something like that, as well as deploying a sensor and making a measurement at a particular location. Now, when the robot's touring around, you could be on a fixed tour. You could tell a robot just to visit all of these locations, make measurements, and then come home. Or it could be smarter. You could actually build in intelligence to it, a bit like a scientist. So it will go out, and if it finds something interesting, then maybe it spends a bit more time there or explores a bit more there before it goes off and does something else. Or maybe it can relay its discovery back to base, and the humans can advise it what it should do next. So there's a spectrum between in-situ sensors and robots, and completely autonomous robots, and humans and human-assisted robots. It's quite an interesting and rich technology space. So homework for those of you who are interested in collecting data, think about what's the operating domain. Is it a robot that flies, walks or wheels across the land surface, floats across the water surface, or goes underwater? How long a mission does it need to have? Is it hours or weeks? What kind of sensors would you like it to carry? Would you like it to do physical sampling? And if so, what kind of physical samples would you like to collect? And then how do we handle the data? Do you want the data streamed back in real time, or do you want the data recorded on the robot and it brings the data back when it returns? And then the problem of how do we analyze the huge amount of data that robots and sensors can potentially retrieve? So quick introduction to robotics, hopefully put it in the context of what we're trying to do in SAEF, and really happy to have questions or discussions with you about what it is you're looking for.